going to start today's lectures by telling you about the Hayabusa2 mission and taking you on the journey that returned a sample of an asteroid to Earth. So Hayabusa2 was launched at the start of December in 2014, and it was launched on JAXA's H2A rocket. And then it travelled to a small space rock, an asteroid known as Ryugu. Now, before we arrived on Ryugu, we didn't know really much about it. In fact, this was our best guess of what the asteroid looked like. This is a model based on the reflected light that could be seen from Earth. And as you can see, it's pretty featureless. You can't see really any details about the surface. You can't see any details about the surface, and indeed even the shape isn't really very clear. So it wasn't until Hayabusa2 arrived, there we go, in June 2018, that we finally saw what the asteroid looked like. And we saw for the first time a tiny new world and actually were able to look at its surface. Now you might say, well, that surface is rather fine, and we can take a look at a bigger image. This is the image taken by the Hayabusa2 spacecraft at a distance of about 20 kilometers away. Now, if we look at the details of the surface, you see lots of craters, lots of boulders. Let's look at those boulders. The green dots all mark boulders larger than 8 meters in size. And that all looks quite exciting until I tell you that the main goal of the Hayabusa2 mission is to find a place to land safely, gather a sample, and return to Earth. And if you go wrong at any point during this process, you would lose the spacecraft and end the mission. Whereupon you might start looking at all those boulders and feel a bit more like this. But maybe it's not so bad. Maybe it only looks this dangerous at 20 kilometers away. What if we looked a bit closer at the surface? Surely then we'll find the perfect place to land. So on board the Hayabusa2 spacecraft were 2 little Minerva rovers, and they're only about 20 centimeters across. And the purpose of these rovers was actually just to hop. They're technology demonstrations for moving on the surface of an asteroid. So the gravity on Ryugu is so low that wheels and caterpillar tracks don't work. The friction isn't enough. So instead, these little Minerva rovers had a weight that turned and snapped back. And as it snaps back, the rover hops. And they're solar powered, so every time their batteries charged up from the sun, they started to hop. And these little rovers, one lived about 113 days, and one lived just 10. And what we think happened, because they went silent, what we think happened is they hopped into a shadowed region. And once they were in the shadow, they couldn't recharge anymore. And so they went silent. But they were equipped with cameras. And what they saw was not this CG animation here, but rather they saw this, which, as you can see, is a pretty treacherous landscape, still full of boulders and rocks. And one of them actually took a short movie. This is actually a series of 15 clips, and it was recharging in the sunshine, and you can see the sun move across the Ryugu sky. So it's like a day on Ryugu. So amazing images, but absolutely terrifying if you're planning to land a spacecraft. But maybe we just got unlucky. Maybe the Minerva rovers landed in a particularly difficult place, and other parts might not be so bad. Well, on board Hayabusa2, was also a small lander known as MASCOT, the Mobile Asteroid Surface Scout. And this was a shoebox-sized mini laboratory built by the French and German space agencies. And it was designed to land on the Ryugu surface and do some science actually on the asteroid surface. And this didn't have solar power. Instead, it actually had a battery which guaranteed power for a fixed period of time. And actually, the battery exceeded all expectations. I think it was designed to last 12 or 13 hours, and it actually lasted 17, so it did really well. But it was also equipped with a camera. And unlike this lovely CG landscape, MASCOT saw this, which, if anything, is even more terrifying. So by this stage, this was now late 2018. MASCOT, I think, landed early October. And I suspect if you were on the team trying to find somewhere for Hayabusa2 to land, you might be feeling a bit like this. And you might say, why? Why do this? It's obviously very dangerous. If something goes wrong, you lose the spacecraft. Also, bringing a sample back to Earth greatly extends the time for the mission because you have to do that round trip. So really, when things look this bad, why would you attempt a sample return mission from such a dangerous surface? Now, to understand why it was so important, we need to go back in time to when the sun was just born. Now, around a young star like our young sun, there is a disk of dust and gas known as a protoplanetary disk. And we actually see these with telescopes. In the top right, that's an image of a real protoplanetary disk captured by the telescope ALMA. And inside these disks, we start off with microscopic grains of dust. And these collide and stick and get steadily larger and larger and larger, and eventually start to look like a planet. Now, there's one complication to this process. If you are forming close to this new, brand new, very hot star, you are going to be much, much hotter than if you're forming further away. And what this means is there comes a point where water vapor freezes into ice. And we call this the ice line, or sometimes the snow line. And the reason this is important is that if you're forming closer to the sun than the ice line, you're expecting to form out of dry rock. There's no ice there. On the other hand, if you form further away, outside the ice line, you will build your planet out of rock and ices. Therefore, planets forming here are expected to be dry, without really much water. And planets forming out here would be wet, consisting of a lot of ice and water. But here is the mystery. We think the Earth formed here, inside the ice line, which means you might ask, how did we get our oceans? And this question is really important because all life that we know on Earth needs water. So asking where our oceans come from is also the same as asking, how did our planet become able to support life? And there are a lot of theories for how this happened. But one theory is that the icy rocks that were forming outside the ice line became slingshotted or kicked into the region where the Earth was forming. In particular, giant planets like Jupiter, Saturn, Neptune, and Uranus have so much gravity. They're really good at throwing rocks. I'm going to try and not throw my phone. Throw rocks towards the inner planets. And when that happens, they might have delivered our oceans. But can we test this? Well, one question we can ask is what happened to the rocks that did not hit the Earth? Where did they go? So these giant planets are throwing rocks everywhere. Not all of them will have hit a planet. So where are the spares? And for that, let's go forward in time to our current solar system. So this is our solar system today, and we can see quite quickly there are two reservoirs of rocks. There's the asteroid belt between Mars and Jupiter, and there's the Kuiper belt out past Neptune. And these are full of rocks that didn't make it into planets. And they're a little like the leftovers when you're making flat pack furniture. So out of IKEA or Nitori, you always end up with screws and bolts that didn't quite make it into your furniture. These are the planet screws and bolts. And unlike the planets, they haven't changed a lot since they first formed. Now, the asteroid belt is still quite far from Earth, and it's a long trip, but we can cheat a little. We can visit something called a near-Earth object, or NEO. And this is an object that probably was once in the asteroid belt, but due to a collision or a push from Jupiter, ended up on an orbit closer to the Earth. Now, these can pose a threat to the Earth, but most don't. They're on orbits that will not hit us, but they are closer, and we can take advantage of that. So this was the idea for the Hayabusa2 mission, to leave Earth and go to an NEO, land, collect a sample, and bring it back to Earth. And the reason you want to return that sample is no matter how great the instruments are on board your spacecraft, they are never, ever anywhere as good as a laboratory on Earth. So if we really want to study these rocks and find out what formed the planets at the beginning of the solar system, and maybe where our water came from, we need that sample in a laboratory on Earth. So despite all the difficulties, this challenge was worth it, and the team were successful. This is a movie from the first touchdown, and we're going to be looking down that sampler horn. So the camera was Cam H, a small monitor camera, and it's looking down that extended sampler horn. And the sampler horn is going to touch the surface of the asteroid. It's going to fire a small metal bullet into the surface, stir up the material, which will rise up the sampler horn and into the sample capsule. And the camera was actually not part of Hayabusa2's initial payload. Instead, it was actually donated through crowdsourcing. So it's a donation from the public. And it's produced some of the best images Hayabusa2 brought back. So this movie is sped up by a factor of 5. And we see Hayabusa2 descending. And go on. There we go. And it's instantly rising, and you can see the material flying out from the site it just touched. And that was the first sample. Now, the team did not just succeed in doing this once. They did it twice. And you might reasonably ask, why? Why would you attempt to do something that dangerous twice? Because let's remember, there's now even more to lose. If something had gone wrong on the first touchdown, you'd lost the spacecraft, the mission's ended. But if something goes wrong on the second touchdown, you lose the spacecraft and a perfectly good sample you've already got. So it was a huge risk. And there was a lot of debate on the team about whether you go for the second touchdown. Do you? Don't you? Was it worth that risk? And to understand why it was, we have to look at what can happen to asteroids in space. So in particular, we have to look at something called space weathering. Now, when we think of weathering on Earth, we normally think of it being due to the atmosphere or to rain. And of course, Ryugu has neither of those things. But it can still be affected by things going on in space. In particular, solar radiation can effectively sunburn the asteroid. Cosmic rays contain even more energy and can also cause changes to that asteroid's surface. And as we saw, Ryugu is full of craters. So micrometeorites come down and hit the surface, and they can heat the surface locally and change its composition. So this means that Ryugu might very well have a skin that is slightly different from the rest of the asteroid. And if you're trying to understand the material that formed the planets, you don't really want to see this skin, ideally. So not only did the team want a second sample, they really wanted one from below the surface. Which brings me to the small carry-on impactor. And this was an experiment to form a brand new artificial crater on Ryugu. So let's look at another CG animation. So Hayabusa2 was carrying a 2-kilogram copper impactor. And what this did is it dropped it, and then the spacecraft went and hid. So when the crater was created, you expect a lot of ejecta to come off the asteroid's surface. And because this might have hurt the spacecraft ran and it hid behind the asteroid. And while it was safely out the way, the impactor exploded and shot towards the asteroid's surface and created a brand new crater. And then Hayabusa2 gathered that material. Now, it didn't land exactly in the crater because that was a bit too dangerous. Instead, it landed close by where we could see that ejecta from that new crater had been gathered. So the CGI does show it landing in the crater. Actually, it landed a little bit further away. And this is the second touchdown. Now, I should mention that before the mission, the team were hoping for a space of roughly 100 meters that would be flat enough to land in. The first touchdown, they only had a space of 6 meters. For the second touchdown, it was even less, and they still did it. So it's incredible. And they ended up with 2 samples that were stored separately in the spacecraft, and they brought them home. So 18 months after the spacecraft arrived at Ryugu, it headed off for home in 2019, November 2019, and it arrived back at Earth at the start of December 2020. Now we have to check and see if this plays. This is the night sky above Woomera in Australia. And what we're waiting for is a sample capsule to enter the atmosphere, because when it does, it will heat up, and like a shooting star, we'll see it move across the sky. And I have to check that video is playing. It's very hard when you're looking at the night sky. But on the right, we should see a bright dot that starts to move rapidly towards the left. There it is. And that's the sample capsule coming home. It's coming through the atmosphere. It's heated up, and it's a bright streak in the sky. Now, more clearly, we can see it with some long photography. So on the right, the very long streak is a sample capsule coming back to Earth. The small streak just above it is a Starlink satellite. And then on the left are 2 images from finding the capsule. The top one is the image from the air, where the parachute in the capsule is seen. And then the lower one is them collecting the capsule off the ground. Now you'll see the person actually touching the capsule is in protective gear. And this is because the parachute was released using pyrotechnics, explosives. And there was a possibility that not all the explosives had gone off. So just to be careful, the first person to touch the capsule had to be in protective gear, but there was no problem. Now, we want this sample to be as pristine as possible, And that meant the team had a time limit, because the longer it remained on the Earth's surface, the higher the chance there was of contamination from Earth. And especially if you want to understand how life began and compare water, the last thing you want is contamination from Earth's water. So the team had 100 hours to find the capsule, collect it from Australia, bring it back to Japan, and secure it safely in the laboratory at JAXA. And they managed it in 60. So this is a scene from the curation laboratory, obviously speeded up, where they're examining the Ryugu sample. And the Ryugu sample was opened in vacuum conditions and then later studied in pure nitrogen, which is a very unreactive gas. So it shouldn't change at all while in that nitrogen environment. And the sample looked like this. This is a sample from the first touchdown. You can see it's incredibly black. So for the mission to be successful, the team needed to return 100 milligrams. That was enough to do the analysis they need to do. In fact, the team returned 5.4 grams, which was fabulous. Now, 60% of that was instantly stored away in vacuum conditions. And this is for future analysis. So it's for analysis by technology that we haven't yet invented, which is an amazing attribute for sample return. So it's also been true of the Apollo missions. The Apollo moon rocks have been studied by technology that wasn't invented during the first moon landings, asking questions that we hadn't yet thought to ask during the moon landings, and examined by scientists who weren't born during the moon landings. And this sample will be the same. We're storing it away for future reference. And the rest underwent an initial description, where the team took the grains and catalogued them. They looked at their size, they looked at their mass, and they looked at their basic composition. And the catalogue is open. You can go to this website and browse it yourself and choose your favourite grain. And from there, the sample has been studied by groups from all over the world. So, what have we found? Well, it's still very early days. At the moment, the initial analysis is still wrapping up. There's been about 16 research papers so far published, but many more are due this year. So we've still a lot more to learn. We've really barely begun. However, there are a few trends, which I'm going to briefly talk about. The first thing is the chemical elements in the sample. So this is just looking at the relative amount of oxygen, of hydrogen, of nitrogen, etc. that are in this sample. And what was found is this is really, really similar to the sun. And this is important and very exciting, because what it means is that if Ryugu is very similar in composition to the sun, it must have meant it was formed around the same time. That is, it was formed while the planets were forming. So this is really pristine material that genuinely went into building the planets that we see today. So it really is one of these leftover nuts and bolts from the very first stage of planet formation. The second exciting result is from a paper by Nakamura et al. And they looked at crystals of iron sulfide and found that these crystals had tiny inclusions of water inside them. And when this water was examined, it was found to be water, but also carbon dioxide, which means this sample, Ryugu, must have formed where it was possible for both water and carbon dioxide to be frozen, so it could be incorporated into this rock. So, not only did Ryugu form when the sun was forming, but it formed much further out, a long way from where the Earth is today. Now, that doesn't mean that it definitely brought the Earth's oceans, but it does mean that material was mixing through the solar system and there definitely is a transport mechanism that brings ingredients from the outer solar system to the inner solar system. Now, I'm not going to talk more about what we could find because I'm going to leave it for Hiro-san's talk to discuss what we know about, what we can learn about such space rocks. Instead, I'm going to look at what comes next. So Hayabusa2 itself dropped off that sample capsule, but it did not return to Earth itself. Instead, it went back to deep space for the Hayabusa2 extended mission that's called Hayabusa2 Sharp. And if you picked up a sticker from outside reception, you should see that's for the extended mission. So Hayabusa2 Sharp is off to another asteroid, one called 1998 KY26. Very catchy. But it's not due to arrive until 2031. So this is a long, long extended mission. But it's going to be worth it because this asteroid is completely different from anything we've ever seen before. For a start, it's tiny. It's only 30 meters across. Ryugu, by contrast, is about 1 kilometer across. But despite being small, it's spinning super fast. It rotates roughly once every 10 minutes. Ryugu rotates roughly once every 7.6 hours. And of course, the Earth rotates once every 24 hours. In fact, this asteroid is spinning so fast, we don't even know how it stays together. It should be disintegrating, but it's not. So that's the first exciting thing, visiting an asteroid type we've never seen before. But just to add a more ominous tone to the proceedings, this size of asteroid, around 30 meters, is statistically reasonably likely to hit the Earth. We expect a collision. I'm not sure when we expect a collision. Hopefully not soon. But it is statistically one of the more likely sizes. And if it does, it will cause a lot of damage. Killing, if it goes to a populated area, it's going to be serious if it goes to a populated area. I think there was a similar impact in Russia, in Chelyabinsk, and it killed over 1,000 people for a 30-meter asteroid. So learning about these asteroids is really important because one day we might have to deflect one. So that's the Hayabusa2 extended mission. Now, sooner than that, we have another mission, the Martian Moons Exploration Mission, or MMX. And this will launch in the fiscal year 2024. And MMX is not going to an asteroid. Rather, it's going to the Martian moons, Phobos and Deimos. And the plan is to return a sample from Phobos and bring that back to Earth. And these moons will also tell us a lot about habitability. In particular, Mars itself is a planet that might have been habitable in the past, but lost its habitability. And some of that information may be preserved on its moons that haven't changed since the early days of Mars itself. So the sample may tell us about how a planet becomes habitable, or even how a planet becomes uninhabitable. So then I just want to say, please do stay in touch. We have a lot of information in both English and Japanese. There's the general ISAS Twitter feeds, and for Hayabusa2 and for MMX with web pages, and also our blog and curation news on the Hayabusa2 sample. So I'm going to slide in a sneaky slide that I didn't tell anyone about, because I know I have a couple of minutes left. And this is because we have stickers that I hope you saw just outside. Please do collect one. This is for the Hayabusa2 extended mission. And as you can see, this is Hayabusa2 Sharp. And the Sharp stands for Small Hazardous Asteroid Reconnaissance Probe, because it's going to look at an asteroid type that might be dangerous or might be like one that is dangerous. And on the sticker, you can see 2 asteroids. This one is the final rendezvous I mentioned, 1998 KY26. And this one is 2001 CC21. It's another asteroid, and Hayabusa2 will make a swift flyby past this asteroid. So it won't stop, but it's going to try and take some photos and get some information while it's flying by. And that is everything. Thank you very much.